Yes. So this team worked on short-term and more event-based landsliding, and we'll show some of the tricks that they had to pull to make that happen.
Thank you, Irina. Welcome everyone to our group presentation. So our project has two parts. In the first part, we try to explore how the landscape gets modified by short-term mass wasting scenarios. In the second part, we try to appreciate the fate of a single landslide event undergoing mass wasting processes. Sorry. Well, so first we synthetically simulate a landscape using LandLab, and we are considering a very active tectonic settings having uplift rate of 4 millimeter per year. And we also considered a closed system having open system having one outlet. And we let our landscape get evolved for millions of years. So this is the final topography we get. And then we applied 200 years of mass wasting scenario on this topography. So we utilized two components of the LandLab. One is priority flow router, and another one is bedrock landslider. So priority flow router um, uh, allows the terrain to experience the flow accumulation from, not only from single direction, but from multiple directions. And so bedrock landslider actually uh, uh, shape the terrain through landslides and sediment transport. You can also see we have defined the friction angle, cohesion, and also critical slope. That actually defines the shear strength of the slope forming materials. So we run a 200-year mass wasting scenarios having 100 years of return period. So our study area is actually experiencing numerous landslides, you can see, having different size and frequency. So this is the results. We can see the zone of the erosion from where the sediments gets eroded by landslide, and we can also see the zone of deposition. Then we actually plot this erosion and deposition on hillshed for better visualization. And finally, we can see the scenario of the landscape that we investigated. So after 200 years, this is the scenario of the landscape that we explored, and we can also see the soil depth. Yeah, now the summary will be explained by my groupmate.
Hi, everyone. Actually, we also did model sensitivity tests by changing key model parameters. And the first of all, we changed, we try all odd number and even number for number of the rows and columns of for the grid. And we found that the odd numbers experience more number of the landslide, which is the odd numbers was 49 by 49, and the even number was 50 by 50. This is mainly because the odd numbers has a central node and it allows it to have a symmetrical topography and flow convergence and leading to higher slopes. And as a result, it's experienced more number of the landslide. And we also tried the open system with the one outlet and the closed system. We found that the open system with the one outlet experienced more number of the landslide, while the closed systems has no number of the landslide. This is mainly because that the open system actually experience higher slopes and faster erosion and quicker response of the hydrological processes, leading to more number of the landslide. We also changed the uplift rate, and when we increased the uplift rate, we found that the number of the landslide increases because the uplift rate increased the slopes and also increases the gravitational force and make the landscape more unstable as a result. So it leads to more number of the landslides. And the last but not the least, we increased the soil slopes, and we saw that when we increased the soil depths, this result to more number of the landslide. And actually, soil depths, increasing soil depths, meaning that weathering activity is going to happen and lead to more number of the landslide. I'm going to present.
Hello, everyone. Like my groupmate mentioned, under the same umbrella of short-term landscape evolution in response to mass wasting event, I essentially shift the focus from like a topography scale over 200 years to one particular hill slope and a single mass wasting event. I decided to, like every good tutorial, there is an introduction part with debris flow channels related to earthquakes, from the Wangshuan earthquake. We have this from the Bear Canyon in Arizona due to a rainstorm, forest fires. So lots of factors can initiate a debris flow in a hill slope, right? So we really wanted to use the mass wasting runout. It's a relatively new package that's been included into LandLab. What it does is essentially creates a downslope progression of mass wasting sediment and allows the sediment to essentially flow through the slope. So with that in mind, I chose a synthetic terrain. Let me just scroll to it. Yeah, so this is how it looks like. It's a varyingly converging concave terrain with the topmost part essentially being the nodes where the landslide would be initiated, right? And when we run the mass waste routing on it, we essentially lead to a debris flow channel being formed with the sediment from the initiation stage being moved through the channel itself, right? Now the thing is, with MWR, the shape of the arrays of the nodes created make it slightly tricky to use it with common packages such as Channel Profiler. So under supervision from our mentors, we kind of went on a roundabout way of analyzing the evolution of this. What we did is we essentially adopted the topography that was created, recreated the grid to make it to obtain the topographic elevation and the soil thickness, and essentially recreated the topography into like a grid that works with channel profiler space, priority flow routing, and other suite of packages. And after initiating the parameters that run these packages, I think I have an example run. Here I'm only simulating, debris flow channels are pretty quick. So I'm only simulating for like 50 years. The background uplift rate is 0.1 millimeters per year. I've set the diffusivity for the depth-dependent Taylor diffuser to be 0.01. And space is essentially has a sediment erodibility of 0.01 and bedrock erodibility, which is much lower comparatively, representing the hill slope. And we essentially arrive at this. So all the sediment, close to like 2.5 meters in average, deposited from the upstream to downstream, actually is removed from evacuated from the channel within 50 years. Based on this plotting function, I also try to explore the model, create exercises for the tutorial. What happens when we change the hill slope diffusivity to, let's say, we already saw the case for 0.01, but what happens when it's like 0.1? Turns out with the diffusivity coefficient, it doesn't really change too much. It still takes close to 50 years, right? But it's pretty awesome when we change the sediment erodibility. When it's like 0.001, it barely changes over the 50-year time period that we have. But if we change it to 0.001, it cleans out within like 30 years, right? That's essentially letting it be more mobile moves it out of the system. So there's a lot we can do. I mean, there are multiple models being involved, lots of parameters that we can play around with. So we can explore the tutorial. And before I end, I'm Shayan. This is Dewan. This is Fatima. We thank the CSDMS team and our mentors. It's been a great, great experience. And that's it.